This video is going to essentially be a culmination of some of the stuff that we've been talking about in previous videos with what the first derivative and second derivative can tell us, how to find local maxes and local mins, concavity, inflection points, all that kind of stuff. Essentially, all we're doing is just putting it all together into one example. So there's really nothing new here, but I'm going to work through an example in this video and alongside of that try and talk about how to do stuff in general. That way when you start diving into things, you'll have some kind of pointers and keys to help out. So anyways, we're going to start with this example here. Take a look at this crazy rational function, and using this function, we're going to recap how to find the domain of a function, how to find the x and the y intercepts, vertical and horizontal asymptotes. We could find the slant asymptotes if you want. I don't really care about those, to be honest, so I might remind you about how that goes, but you can find all this information elsewhere. This is stuff that we've already talked about in algebra classes or in calculus class already. After that, we're going to start diving into this kind of like newer stuff. We'll talk about when this function is increasing and decreasing, find local maximums and local minimums. We'll find out when the function's concave up or down, and find inflection points. So this is our function. By the end of this video, we should have a pretty accurate sketch of this function. First, we're just going to analyze the function itself. So this is all review. We're going to find the domain of our function. This is just the set of possible inputs. What we're really looking for here is division by 0 or square roots and negatives, or natural log of 0 or negative. So if we have something like that in a function, we might mess up the domain. So we'll look for any of those problems, and then we'll say, okay, the domain is going to be everything else. For some of these functions, it's going to be super easy because we might have a polynomial function, and we'll say, well, okay, this is a continuous function everywhere, and so that means the function exists everywhere, so the domain is everything. With our example, we'll talk a little bit about it, but this is basically going to be different for every problem. We're looking for all the possible inputs. This is going to be super helpful. To find the x-intercepts, we're really solving this equation. Set the function equal to 0, figure out where our y values are 0, what x values are going to do that for us. To find the y-intercept, we're really just evaluating our function at 0. There may not be a y-intercept depending on what the domain is. There might be multiple x-intercepts. There might not be any depending on what the function is. So we might see these kinds of things. For vertical asymptotes, we're really looking for where a limit as x approaches some value a from the left or from the right is equal to positive or negative infinity. And you might remember that this shows up when you divide by 0. So that's going to really pop into play when we see the domain. Domain and vertical asymptotes are really going to go together a lot because a lot of the problems that we find in our domain are going to be these vertical asymptotes. And then for horizontal asymptotes, we're really thinking about what happens to our function as x goes to positive or negative infinity. Does that equal an actual value? What do we have going on there? These are all old things that we've talked about. The vertical and horizontal asymptotes, you may not have seen anything really formally about them until this class, but we've talked about it all previously. So let's just kind of go through this for this function. Here's our function. So if we think about domain here, this is a rational function. That means for the domain, it's really, where are we dividing by 0? So I might rewrite this function out. I might call it 10x cubed over, and then I'm just going to factor x plus 1, x minus 1. And then we can see these problems with division by 0 at positive or negative 1. So we'll say everything from negative infinity up to negative 1, from negative 1 up to 1, and from 1 to infinity. You can use these union symbols to put these things together. Or if you want, you can say all the x values except plus or minus 1. This is going to be really important for us later on. It's going to be obviously a really important part for graphing this function to get an idea of what's going on here. For our x-intercepts, we're going to try and set this thing equal to 0. So we'll say 10x cubed over x squared minus 1 equals 0. For a rational function, we really only have to look at the numerator, because for a fraction to equal 0, that means the numerator is equal to 0. And we can see pretty easily that that's at x equals 0. So we've got these problems at plus or minus 1 in the domain, but we cross our x-axis at x equals 0. For the y-intercept, we just look at f of 0, and we'll see that's 0. And so really, and this is obvious hopefully when we found this x-intercept, really we just know that this function is going to go through the origin. For vertical asymptotes, we're going to look at where we divide by 0. That's right here and here, these two factors. And so minus 1, and positive 1. So these problems in the domain are vertical asymptotes. So that's something to keep in mind. And then for a horizontal asymptote, we can take a look at the limit as x goes to infinity of 10x cubed over x squared minus 1. And we can see really easily that this is not going to be any value, a real number. It's going off to infinity. Hopefully you remember that you can look at first terms and or biggest terms of polynomials. I hate the way that I've drawn that. And this too. Let me just fix this whole thing. There we go. That's better. And we can say this is really like 10x cubed over just x squared. So it's really 10x. And as x goes off to infinity, this thing goes to infinity. You could find a slant asymptote by saying the degree on top is bigger by 1. So you could use long division if you want to rewrite this polynomial as some linear function plus a remainder. And then the remainder will get tiny when x gets big, and so it'll just act like a linear function. I really don't care about that, to be honest, though. So I'd say don't worry about it. If you want, you can look that up in the text. I think they've got an explanation of slant asymptotes. So there's a whole bunch of information about our function just from this example. Then what we have to do is analyze the function f. Or f prime, sorry. So f of x is 10x cubed over x squared minus 1. So first we have to think, okay, how are we going to find the derivative? What is the derivative of this kind of a function? And hopefully you'll notice really quickly that you're going to have to do quotient rule. So I'm going to pause the video. I'll let you spend a minute or two finding the derivative of this thing. You might have it written in a couple of different forms. I'll collect you back later. So pause this video, work that derivative out, make sure you can remind yourself how it goes. Go. All right, so hopefully you've got something that looks like this. I just went through the quotient rule really quickly, and hopefully you can kind of follow that through doing the distributive property, collecting like terms. What I'm going to do, and you'll notice I didn't multiply out the denominator. What I'm also going to do is factor in this top. I'm going to notice that 10x squared is a common factor here. And so what we're really going to have is x squared minus 3. You hopefully can see why that's going to be really important. This is going to make it easy for us to find critical numbers, or at least easier. So this is the derivative that we're going to analyze. This 10x squared times x squared minus 3 all over x squared minus 1 squared. Now later on when we go to find the second derivative, I'll probably use this version of it simply because it's going to be easier for me to find the derivative of the numerator in this than it is over here with it factored. I have to do like a product rule or something like that. So it's nice to have both versions on hand, but let's work with this. We'll analyze this one and use this to find f double prime later. So when we find the second derivative, I'll probably have to skip back a couple slides to remember what this looks like, or I'll just multiply that out. But anyways, let's move on. So we're going to analyze our first derivative. And in general, these are the things that we're looking for. We're looking for critical numbers. Now, we're really looking for values where the derivative is equal to 0, or f prime of x doesn't exist. And we're going to have to check with the domain. Meaning, we have to remember that critical numbers are all supposed to be, I think we called them like interior points in the domain. We said they have to be in the domain and not ending points, right? So if we're going to be checking critical numbers, make sure that we go back and look at that domain. That's why it's really important to actually find that at some point. When we do our sign chart, we're going to use all values of f prime of x equal to 0, or say x with f prime. Let me fix this because I wanted to change the wording after I started. So here I'm going to use all values of x where f prime of x equals 0 or f prime of x doesn't exist. So what we're going to notice for our example is that we have these two vertical asymptotes. Clearly, our derivative is not going to exist at those vertical asymptotes, but that's not because of anything interesting about the derivative. It's because the function doesn't exist there. So we're not going to call them critical numbers, but we still are going to split our sign chart up there because those are spots where the sign of our first derivative can still change, right? We can still have a positive to a negative or negative to a positive. Now, since they won't be critical numbers, since we're not actually looking at points on the graph, we're not going to use the first derivative test on these vertical asymptotes. So what really I'm going to do is in the sign chart, I'm just going to try and denote the vertical asymptotes just to try and keep it in my mind that, okay, even though the first derivative test looks like it applies, these aren't critical points, and so it's not actually going to work. So for the increasing, decreasing stuff, we're going to remember that we're looking really at where the first derivative is positive or the first derivative is negative. And then local maxes and local mins, we use the first derivative test. And again, I'm going to say double check to make sure you're talking about a critical point. All right, cool. So let's do it. So we have our first derivative. Go ahead, find all the critical numbers. Now, there's going to be a couple that are going to be a little misleading. So maybe I'll just say first, find the values where the derivative is equal to 0 or the derivative doesn't exist. And then we'll go ahead and build our sign chart, make sure we can tell what's going on with critical numbers, all that kind of stuff. So go ahead and find those. All right, so I just went ahead and wrote them all out here. Values where the first derivative is equal to 0. That's going to be x equals 0, negative root 3, positive root 3. And then the x values where the derivative doesn't exist is going to be negative 1 and positive 1. But we got to be careful because those are not actually critical points. These are the vertical asymptotes. So they're going to show up in our sign chart still, but we're not going to call them critical. That means when we do the first derivative test on here, we'll just have to be a little bit careful about it. So let me show you what I mean. Let's build this sign chart. So we're going to have our x values. We're going to go from negative infinity. I'm not going to write all the intervals. I'll just write them up. Negative infinity up to negative root 3, then from negative root 3 to negative 1, then from negative 1 to 0, from 0 to 1, and from 1 to root 3, and then from root 3 off to infinity. And what I want you to do is to check the sign of the first derivative in here, fill these all out, but first, I want to just be very, very careful, and I want to do this. I'm going to draw these in, and I'll put a little asterisk here that says these are vertical asymptotes. The reason I'm doing this is that if, for instance, my function decreases and then increases after that, I don't want to say that there's a local minimum here. Even though the function might change direction, it's because there's a vertical asymptote there. So I normally try and put these little dotted lines like this and denote what's going on, just so we can really see what's happening here. I might also go ahead and do this. I'm going to put zeros in here for what the first derivative is doing, just to remind myself that all of these are actually spots with horizontal tangent lines, not sharp corners or vertical tangent lines. So later on, when I sketch things, I'll have that information for me. Okay, so go ahead, fill in the signs of the first derivative in the intervals around these critical points and vertical asymptotes. Go. All right, so hopefully this is what you found. I want to notice something. Notice 10x squared is positive no matter what. You're going to square this x value, so that's why I just put a positive sign in here. And notice the denominator, same thing. That's positive no matter what. Sorry, I think that cut out for a second. You're squaring this denominator. So really, all we care about is the sign of this factor here. So we're going to notice that the only time the first term is bigger than the second is when the number that ends up getting squared is bigger than 3 after it's squared. Meaning, root 3 is this kind of cutoff point. Anything between negative root 3 and root 3, like close to 0, you're going to have some small number here, squared, minus 3, that ends up being negative. So the only time it's positive is on the outside spots here. So hopefully that was easy enough for you to find by just checking all these. Let me put in all these increasing, decreasing spots. And let's talk about what's going on here. So first off, we'll say it's increasing pretty clearly on negative infinity up to negative root 3, and from root 3 up to infinity. And then intervals where it's decreasing can be kind of tricky in this one. I'm running out of space. Let me rewrite this. I'm just going to do an I and a D. Here we go. Increasing on negative infinity up to negative root 3, and from root 3 up to infinity, and decreasing, here we go, clearly from negative root 3 to negative 1. And then this is a weird one. It looks like it's decreasing from negative 1 to 0, and then also from 0 to 1. Notice that we're continuous all the way through here. What this is going to look like is this. It decreases, it levels out at a horizontal tangent line, and then it decreases again. Now, this actually fits our definition of decreasing through the whole interval from negative 1 to 1, because this little critical point, we don't change direction, and it's just the single point with the horizontal tangent line, meaning all the y values as you move from left to right actually do get smaller. So you might see it written like this instead of from negative 1 to 0 and from 0 to 1. Now we do split it up at the vertical asymptote because the function's not continuous through there. And then we're also going to have it from 1 up to root 3. Now, hopefully, we can find local maxes and local mins pretty easily using the first derivative test. It looks like there's a max here, and it looks like there's a min here. So let's just go ahead and write that down. There's a maximum at negative root 3 f of negative root 3. We could find out what that is in a second. Maybe I'll grab a calculator or something like that. I probably don't need one. And we'll see what's going on. And this is f of root 3. Cool. So we can find these coordinates so that we can plot them later on. I'll probably just round these off with a calculator later when we go ahead to plot these things. All right. That's everything we need to know about the first derivative. There's a lot of stuff going on here, right? Cool. So now we're going to analyze the second derivative. So what I want to do is go back, and I want to grab this chunk here and say this is our first derivative, 10x to the 4 minus 30x squared over x squared minus 1 squared. 10x to the 4 minus 30x squared over x squared minus 1 squared. I think that was right. Let me just double check. 10x to the 4 minus 30x squared over x squared minus 1 squared. Yeah, perfect. Okay, go ahead and find the derivative of this thing. You're going to have to use the quotient rule again. And notice, to find v prime, you'll have to do a chain rule on this. So keep your heads up. Go ahead and do that. Take a couple minutes, pause this video, and then I'll catch you up in a minute. All right, that was kind of a long one, right? Hopefully you noticed this part right here. There's these nice common factors of x squared minus 1. So from the chain rule, we have this x squared minus 1 times 4x. This 2x is the derivative of the inside part, right? And so what I did is I factored out an x squared minus 1 from everything and canceled it. So our exponent goes from 2 to 1. We lose the term x squared minus 1 here, and then we go from 4 of them down to 3 of them in the denominator. That just makes things a little easier to multiply. And then at the end, you'll notice we've got 40x to the 5th minus 40x to the 5th. This stuff here is negative 100x cubed plus 120x cubed. So we're left with 20x cubed and 60x. And then I just factored again. That's going to make it easier for us to analyze. So we'll deal with this version of it. So that's our second derivative. Make sure you can find that. So in general, what are we going to be doing here? We got to find possible inflection points. So these are going to be the spots where, the second derivative, there we go, is equal to 0, or the second derivative doesn't exist. And we'll again check with the domain. Because we're going to find again that those vertical asymptotes are still spots where the second derivative doesn't equal 0. But when we do our sign chart on this, hopefully we'll make sure that we recognize that they're not going to be inflection points. We'll build our sign chart, and we're going to use the same advice that we had here. We're going to use those values, even the vertical asymptotes. So we'll use all of the spots where the second derivative equals 0 or the second derivative does not exist. Even vertical asymptotes. For concave up or down, we're looking where the second derivative is positive or the second derivative is negative. And for inflection points, we're not going to use the first derivative test or the second derivative test, even though it feels like this should be the second derivative test. We're just going to use the sign chart, and we're going to check where f double prime changes sign. So let's go ahead and do this. Here's our second derivative. Oh no, I forgot to change all these. I'll change them on the slides, but they're going to be the possible inflection points. So let me do this. Possible inflection points. And then instead of increasing and decreasing, we're going to be looking at concave up or down. And instead of local maxes and mins, we're going to be looking at inflection points. I'll go ahead and change that on your copy of the blank slides so that you can see that. So we're not talking about increasing or decreasing here. We're not talking about local maxes and local mins. All right, so let's go ahead and do it. Our possible inflection points right here, when x equals 0 is 1. Here, we could say x squared plus 3 equals 0. That's going to be when x squared equals negative 3, and hopefully alarm bells are ringing because you've got plus or minus negative root 3. So that's not going to be anything of interest for us. But we're still going to have these x equals plus or minus 1. So our possible inflection points, x equals 0, negative 1, and positive 1. We'll say, wait a second, nope. Those are vertical asymptotes. So when we set up our sign chart, we're going to go negative 1, 0, and 1. We're still going to use these, but again, I'll try and denote to myself that these are vertical asymptotes. We still might change from concave up to concave down. Our concavity might be different on either side of these asymptotes. But what we will notice is that they're not going to be inflection points if the concavity changes. So just keep that in mind. So we can take a look at the second derivative here and then tell what our function is going to do. So go ahead and find the signs, fill them in on your sign chart. You should have 1, 2, 3, 4 signs that you look at. The stuff from negative infinity up to negative 1, from negative 1 to 0, from 0 up to 1, and from 1 to infinity. And then we'll be able to take a look at what the concavity is doing. So go ahead and fill that in. So pause the video and do that. All right, so this should be what it looks like. Notice the concavity does change at these vertical asymptotes. So if we didn't kind of note that these were asymptotes, we might get tricked into thinking this is an inflection point at negative 1 and at positive 1, when really the only inflection point is here. So we can go ahead and say we're concave up on the interval from negative 1 to 0 and from 1 to infinity. And we're concave down on the interval from negative infinity to negative 1 and from 0 to 1. And our inflection point is 0, f of 0. And we can find the y value later, although I'm pretty sure it's the origin. Cool. So we've got all this information. Now what we have to do is go back and graph it. So we're going to go back through all those little summaries. We're going to find what were my x-intercepts, plot them. What were the y-intercepts, plot them. Where were the vertical asymptotes, plot them. Was there a horizontal asymptote? If there is, plot it. Where is my function increasing and decreasing, and where are the local maximums and local mins? Draw that in. Where is it concave up and concave down, and where are my inflection points? We'll draw that in. So let me just get a big set of axes here. And we'll start plotting as much as we can. I know there were vertical asymptotes. So let me go all the way back to the beginning. Nope, wrong one. There we go. There's vertical asymptotes at negative 1 and 1. And we have this point at the origin. No horizontal asymptotes. And then that will cover our domain as well. So I'm going to go ahead and graph that. I'm going to put a point right at the origin, 0, 0. That's my x-intercept and my y-intercept. And then I'll plot in those asymptotes. So all the way to the end, here's my point at the origin. Oops, I gotta get that. Let me do it in blue. I'll do my graph stuff in, oh my gosh, I've got this ruler on. There we go. And now I do want that ruler back again. I'm gonna say this is negative 1. I want to maybe make that a little farther. There we go. -1, -2, -3. I'll call that 1, 2. Oh, no. 3. And I'm just going to go ahead and plot these asymptotes here. There's 1. And there's 1. All right. Now I have some points that I want to find. I'm going to go back up to my first derivative, and I'm going to grab these local maximums and local minimums. My function was 10x cubed over x squared minus 1. If you plug in, let me grab this really quickly, -3 into, where's my function? Here we go. I'm going to grab this function here. Oh, no. Oh, I can't select it. Okay, I'll just write it. 10x cubed over x squared minus 1. That's here. Oh my gosh. I'm sorry. Here we go. So if we want to take a look at what's happening at root 3, we can say f of root 3 is 10 times root 3 cubed over root 3 squared minus 1. Now, root 3 cubed is really root 3 squared times root 3. So that's going to be 3 times root 3. So this is 30 root 3 on the top over 3 minus 1. That's 2. So this is 15 root 3. Oops, let me fix that. There we go. Now, all I really care about is that the square root of 3 is somewhere in between 1 and 2. And there's some point up here. Oops, I want to use blue for this. There's some point up here at root 3, 15 root 3. And this is a minimum. There's another point down here at negative root 3, negative 15 root 3. You can go ahead and plug in negative root 3 into this and see what happens. You're going to get a negative sign here, so you get negative 30 over 2 with a root 3 on it. So it's going to end up being the same thing. And this is a max. Cool. I know that I have an inflection point at 0, which is right here. I also know that these two have horizontal tangent lines. So I'll go ahead and draw them like this. So hopefully you can already get a sense of what this looks like. But now, maybe let's just draw this max. I know I'm going to go up to it, hit it, and go down. And I got to go down to that asymptote. I'm going to use red for the graph. So I'm going to end up doing something like this. I drew it as kind of a straight line because I know that there's a linear asymptote on here, a slant asymptote, because we said the degree on top is bigger by 1. But those are small details that you guys can pick up by just graphing things on a calculator or using technology. So that should be fine. Then I got to figure out how I get through this point. So I'm going to go back to my first derivative, and I'll notice from negative root 3 to negative 1, I am decreasing. And from negative 1 to 0, I'm decreasing. Then, sorry, I want the one in between the asymptotes. From negative 1 to 0, I'm decreasing. And from 0 to 1, I'm decreasing. There we go. So on this whole interval in between these asymptotes, I decrease. I've got a horizontal tangent line at 0. So let's go ahead and put that tangent line in here. So I know I'm going to come through. I have to level off and be horizontal. And then I'm going to go down. So now I need to figure out concavity. Well, it's concave up and then to concave down. What that means is that I'm decreasing concave up. Oh, and I want to use red. Oh, that's hard to draw. Let me fix that a bit. There we go. And then it's going to be decreasing concave down. So it looks something like that. And then we said we were concave up the whole rest of the time. And if you go back to the first derivative sign chart, decreasing to increasing. So around this point, we're going to do a similar kind of thing that we did on the right. And it's going to go like that. So here's a pretty good picture of this graph with the inflection point found and labeled, a minimum found and labeled, and a maximum found and labeled. That's a half-hour problem that we just did. long time to go through all that stuff. That's how long this video is. So these are big problems. You kind of know my policy on graphing stuff already. You haven't graphed anything for me on a test or an exam. I might have you sketch some stuff, but what I think is more important is making sure that you just know how to collect all this information and how to visualize it. I will test you on that stuff, but I'm not going to test you on your artistic drawing skills. So things like that slant asymptote, not recognizing that without a graphing calculator, no big deal. I don't really care so much about that. I care about you finding local maximums and minimums, inflection points, knowing what it looks like when a function is concave down or concave up, all that kind of stuff. So I'll try and gather up a couple other examples. I might post some information or talk about things in office hours where we go through some stuff. But really, this is just collecting all the information from the first derivative and second derivative and putting it all together. So good luck. Jump into some of these problems. They're very big. They're very long. Hopefully, it goes pretty well for you.